afternoon, everyone. This is Celso Batalha, Physics to Be. So let's go over chapter 23, magnetic induction. And so I would like to outline or review what we saw in class and work on a few problems. After spring break, we are going to basically initiate geometric optics and then get ready for modern physics, which is exciting too. Um, let's go take a look there. Now, this chapter, as I mentioned, there is a lot of components, especially the AC component. And this AC component we are going to see in your projects. So I have you working not only um, induction and magnetism. I have you choosing some of the components in our lab that has to do with AC and induction and develop a project and then go over some of the course content and theories associated with it. So rather than going through another week with AC, which is probably would be required, and then we can move on to geometric optics as we did. As mentioned previously, induction is a process by which you see current being generated when not just the magnetic field changes, but also a combination of magnetic field and areas where these magnetic field lines having to be passed change it. So in other words, oh, I didn't bring my sheet. Wait a second. There you go. Sorry about that. There you go. So this chapter basically defines. Oh, wait a second. How come it's not on? Okay, so this chapter basically defines what's called magnetic flux. Magnetic flux. So magnetic flux is for us is basically dot product between magnetic field and the area where this magnetic field go through. So imagine you have a circle, right? You have a circle and like a loop, which is a perfect circle, and not only that, you have also magnetic field lines transpassing um, the circle. So these magnetic field lines have a strength at the point where they cross the area. Okay, and let's say if we are talking about a circle, the area of a circle is equal to pi times the radius of that circle squared. If you wanna use a diameter instead of the radius, then you have the area of the circle given by that. But as we introduced magnetic flux, is the dot product between magnetic field and vector area. So what is vector area? So vector area is a vector given by, and remember the definition of what a vector is. A vector is something that has direction and has also magnitude, has a number associated with it. So in this case, the number associated with the vector area is the area itself we are considering. And direction, pretty much you choose. So it is chosen to be the direction of this vector area is chosen to be one that is perpendicular to the surface. So in this case, if we are talking about a circle, the surface is pretty much the surface of a circle, right? And here is your vector area. If we had otherwise a, let's say, a sphere, right? Let's say you have a sphere and you have a shell in this sphere. So this is a sphere, and we are seeing the concave part of it. Um, and and let's also consider there is a magnetic field that passes this sphere like that. Okay, like we did for the circle. Now is the sphere is a 3D thing. So what would be the vector area? Well, the vector area is something that happens to be always um, perpendicular to the surface, and that would be here. Now, if here's the center of this sphere, then the vector area at this point goes like that. That's the perpendicular to the surface, okay? So the perpendicular to the surface depends on where you are trying to indicate the surface area. It's always something perpendicular, makes a 90 degrees angle with the surface, okay? So that as a dot product, and as seen previously in physics 2a, a dot product can be broken down in the product of the two vectors times the cosine of the angle between those two vectors, right? So in my example over here, the angle is 0, right? So because they have the same, both vector B and vector A have the same direction, meaning the angle between them is 0. But if you look at this sphere, it's more complicated. Depending on the direction of your field, so the field is parallel, as I'm indicating here. So it's a complicated issue because the angle keeps changing all the time. And that requires 4B sort of skills because you need to integrate that. Okay, so that's the definition of magnetic flux, and you need that to solve a few situations. Now, what is this important? It's important because of Faraday's law. Faraday's law. So Faraday's law tell us the following thing. Well, if you have a magnetic field somewhere in the space and you have a loop through it, these magnetic fields happen to be passing, then you define magnetic flux. If this magnetic flux is changing over time, so you have a change of this magnetic flux over time, so the negative of it is equal to some electric motive force that happens to arise in the loop itself. And then you see, well, what is going on? So imagine you have this loop over here. Bring the loop again. And let's also assume, as done previously, that there is a magnetic field that passes this loop, and just to make it simple, it goes with an angle of 90 degrees. It's perpendicular to this loop, okay? So let's assume that. So not only that, let's assume this magnetic field B is variable. So variable means it's not constant, right? So it's changing all the time, right? So what this law is telling us, if the magnetic field is variable, and assuming this loop, this ring over here, is kept constant, right? So it's kept constant, it's not changing. Then it means that the magnetic flux is changing also over time, because delta phi is equal final quantity minus initial quantity, and the final quantity of it is B final times A final, and the initial quantity is given by this. So let's say, and just for the sake of making it simple, right? So let's say you have a B that in a time interval given, the initial value of it is 0 Tesla, just to make it simple, right? And the final quantity is 10 to minus 4 Tesla. Again, just to make it simple, I'm creating numbers. And let's say this magnetic field is changing in some progressive way, in some smooth way. Okay. And just for the sake of example, let's assume the area is not changed, which means the loop is fixed. You have a loop there, like a ring, your ring, and the ring in your finger is made of a metal, and it's pretty much constant, right? The size of it is constant. So area is constant, and again, just to make it simple, let's bring an area of your ring. I'm making up a number here, and let's put a 10 to minus 3, right? Square meters, something like that. So if this is true, when you calculate the final product between the magnetic field and the area itself, so you are going to plug your final magnetic field 10 to minus 4 Tesla, and then you are multiplying that by the area. And again, these numbers are pretty much just to help direct your thoughts, and that gives 10 to minus 7 Tesla meter square. Okay, which is a unit Weber, but let's keep moving. And the magnetic flux initial one is the initial magnetic field is 0 Tesla, and the area is also, since it doesn't change, it's the same, so is 0. Okay? So let's say these changes occur in a time frame of, let's say, in a time frame of 1 millisecond, right? 1 millisecond. 1 millisecond. So it's a very short time in which the field kind of went from 0 to 10 to minus 4 in 1 millisecond. 1 millisecond is 10 to minus 3 seconds. And again, I'm just putting numbers so we can try to see what's going on. So if we do that, we find this quantity, which is the symbol of electric motive force. So the electric motive force is the negative of delphi, which is final minus initial divided by the time. And we have something that is 10, negative 10 to minus 4, 10 to minus 4 volts. So the ratio between Tesla meter square divided by time is volts. So in other words, if you have a loop like this, let me design the loop again. But instead of a closing, let's make a circuit. And just for the sake of, let's put a light bulb here, and close the circuit. See what I did? So I kind of broke this up, right? And make a small circuit, right? That's what I did. So for all purposes, I have a circuit, but I have a closed loop. Okay, the loop is pretty much closed there. And not only that, let's also expand on this equation, and that is, let's say I don't have one loop, but I have n loops. I have 300, like the solenoid you saw in the lab, or the solenoid you worked in the lab last week, over 2,000 loops, right? So they are all rounded. They go around and around and around and around and around and around, and then somewhere in one of them you make this opening here, and you connect that with a light bulb. So, which means when you calculate your electric motive force, would be something times n. So if in other words, if we does this exercise with um, the magnet, the solenoid we had in the lab, over 2,000 loops. So we would have basically an electric motive force, which is, again, I'm bringing up numbers, 2,000 times 10 to minus 4 volts. And that is pretty much what? Negative 0.2 volts. Well, negative 0.2 volts is interesting. It's a small voltage. But if you could conceive that the time in which these changes are occurring, or that you have a magnetic field that is stronger than 10 to minus 4, right? Is a stronger magnetic field that you are playing with. Let's say you have a much stronger magnet, right? And you are playing with a much stronger magnet, maybe moving in and out or something like that. So what I'm trying to say is you ended up having a circulating current through your circuit and eventually having this light bulb lighting up, which is fantastic. So we don't have any power supply here. We don't have a motor. We don't have anything. Or a generator. So what we are basically doing is creating a series of loops and providing the means to come up with a magnetic field that is variable. And by doing so, you come up with the voltage like a battery. And then you have currents coming up. Okay? So this is the essential aspect of this chapter on Faraday's law. Now, how do we find the direction of the current itself? So that is, if you use Faraday's law alone to determine the current, what we do is, so you have your loop. It's also a right-hand rule, and I will not do it right here because you cannot see my right hand. It's complicated, but basically what you do, you have your magnetic field. You define your normal vector area. I thought I had in red. You define your normal vector area like that, right? And then what you do, you go through the whole calculation which we just did to figure out your electric motive force, and then pay attention to the final sign you got. See the sign here? Negative. So pay attention to that. So how do we figure, according to Faraday's law, the direction of the current? Here's what you do. So in my example here, I have set the normal vector area pointing to the right, right? So now bring your right hand, and I can't do here, and place your thumb as if resting on the normal vector area. So here's your thumb. And then curl your fingers of your right hand, and again, you have your thumb resting on this normal vector area. That's the thumb. And then curl your fingers as if you're going to grab this vector, right? So, and when when you curl your four fingers as if you're going to grab this normal vector, it gives you a direction of the circulating current. If this is a positive sign, if sign is positive. So if the sign is positive and your calculation led to a positive sign, which is not my case here, and you had defined your normal vector area the way I did, and you put your thumb of your right hand on this vector, and you try to grab this vector, right? By curling your finger, it defines the circulation of your current. This is the circulation of your current. Now, since or if the sign is negative, you go the other way. So if sign is positive, then, no, oh, I'm sorry. If the sign is negative, if the sign is negative, then circulation, current circulation goes the other way, right? So which means here's my loop, here's my magnetic field, this is the normal vector area, and let's take my example now, the one that I really did, the one that really gave a negative sign. What is the direction of the circulating current? Here it goes. So it goes this other way. Okay. Okay. Now this is pretty much Faraday's law. Now Lenz's law, which is also discussed in this chapter, and I wanted you to learn that, is an easier way to figure out the direction of a current. And the way it goes is you have to figure out if the magnetic flux is increasing in your circuit. In fact, I would do this in class because it's easy to be digested. So if you can grab the concept and remember the concept of Faraday's law, so in class, in fact, in lab, when we assess induction, I will review Lenz's law, which is going to be easier to do. But Lenz's law is basically you let's say in this loop over here, we have a loop, and let's say we have a magnetic field, external magnetic field that goes into the loop. Okay, so this is the symbol of an external magnetic field. When I mean external, is created by some device or something outside, and the direction it goes into the page. And let's assume for now that it is growing. It is growing. Okay? Like the one that I defined previously. So it started with 0 and then it goes to 10 to minus 4. So it's growing over time. So if this is true, it means the magnetic flux inside the loop. So if this is true, the magnetic flux inside the loop is growing. And if this happens, Mother Nature, which means the loop itself, Mother Nature works in such a way that, and let me bring some different color. Mother Nature works in such a way that this loop creates a current that creates a magnetic field of its own that works against that growth. In other words, creates what we call induce the field, induce the field, induce the field, and what it does, it balances out the growth in magnetic flux, which is pretty much created by external agents, right? So the loop itself is not external. The loop itself creates a current that induces a magnet or generates itself a magnetic field that it will counterbalance this external growth. So the field is pointing outside. So the question now is to figure in which direction the current should flow so this field can be created. This is the induced current. So the induced current, induced because of what? Well, because you have some, is induced because you have some external magnetic field that is growing and therefore growing the flux, the magnetic flux inside the loop. So what the loop, what Mother Nature does, it creates a current in the loop in which, in such a way that this current, because if you have a current, as we studied in the previous chapter, if you have a current, you have a magnetic field. So this current induced by this growth in magnetic flux, this current induced itself creates this magnetic field. Okay, and then there in that way you have determined the direction of the current. Like, so let's apply Glen's law for my example, the example I did previously. So we know the result. The result was, well, the current should be counterclockwise. No, clockwise as we look in this direction, clockwise, based on the given situation. So let's see if that is true. So how do we know? Well, so we have a field that is growing, put in black. We have a field that is growing in this direction, right? So the field grows in this direction, which means the loop itself creates a magnetic field that opposes that growth, so goes in the opposite direction, be induced. The question is now, okay, this induced field, what is the current creating it? What should be the current creating this induced field? And the current, how do we figure the current? How do we figure that? So to figure the current, what do we do? Well, we place our thumb in the direction in which the current flow, which is this way. So put your thumb right here, and then curl of your right hand, of course, and then curl your fingers, and the direction of your fingers tells the direction of the magnetic field induced, and then we got that one. Okay. All right. So again, let me now focus on some problems.